welcome to this final week about functional programming in OCaml. So, what do we have so far? We are able to define top-level types, functions, and basic values. So what we have done is to program in the small, which means that we have defined very fine data structures and algorithms. And what we have seen is that OCaml, the core language of OCaml, is great to write these data structures and algorithms in a safe, sound, and efficient way. So now, when you have to deal with the development of a large project, you have an extra difficulty, which is to manage the complexity of your system. That can come from the high number of definitions. The problem is that sometimes in a large system, you can be lost into the implementation details. And an answer to that problem is what is called abstraction in software engineering. An abstraction is a concept then that can be understood intrinsically without a precise knowledge of its implementation. So it's a way to forget about the details and understand some part of the system by itself. An abstraction can be built on top of other abstractions so that the system is built using some vocabulary that clearly describe the answer to some problems at some level of abstraction. In fact, when you design a software, good architecture are made of layers of abstractions. So the rules of the game are different now, and what you want to do is really different from what you do when you implement algorithms. The first thing that you want to do is to be able to split the system into smaller components that can be understood separately and also delegated, whose development can be delegated to several programmers. Then you don't know if two programmers won't use the same name, so you want to have a way to avoid conflict. Also, you want the software engineering to be respected, which means that a programmer is not allowed to break the abstraction, to go into details that he should not know. And also, a good property of components is their ability to be recomposed, reconfigured after their development. In fact, the module system of OCaml fulfills all these requirements, and that will be the topic of this final week. So we will see how to structure software with modules, how to hide information. We will do a small case study about how to design a library for dictionaries. We will give some basic notions about what functors are. And finally, we will see how new modules can be used to compile and produce a large executable program. The first thing to know is that a module defines a namespace. So we already saw that the dot notation can be used to access a module component. When you write list.length, it is a reference to the length function, which is defined inside the module list. Now, if you want to avoid writing this list.something, it is always possible to open the namespace of a module list to implicitly refer to list.length when you write length. So just by writing open list, you can be in that setting. Now, if you open two modules and they define identical identifiers, then the last one will have the priority. So now, how can you define a module? The syntax is the following one. You use the keyword module followed by the identifier for this module. And between struct and end, you just write a sequence of definitions that will be part of this module. The thing that you have to know is the fact that the identifier of a module must start with an uppercase letter. Then you can just write definitions as you already know, value, type, exception definitions inside the implementation of the module. Sometimes you may be interested in changing the name of a module for some reason, so you can also alias a module just by writing module, one identifier for the module you want to define, is equal to another module identifier. So let us see what module implementation looks like in OCaml. So we have this module keyword that introduces a module. Here we have named this module stack, and we used an uppercase letter to start the identifier. And between struct, we have implemented several functions and types that implement the data structure of stack. So we know that the stack is implemented here by a list. The empty stack is the empty list. Pushing an element on top of the stack is adding an element at the beginning of the list. And if you want to pop the element that is on top of the stack, then it's not possible if you have an empty list. But if you have a non-empty list, you can just return the head of the list, and the new stack is the tail of the list. So if we evaluate this, we can see that OCaml accepts this definition and infer what is called a signature, which is in fact the type of the module, and it describes the declaration for types, for example, but also what are the values provided by the module. Here we can see that there is a value empty of type alist. We can use the module using the dot notation here to extract the empty list, here to push an element on top of the list, and here, for instance, to pop an element of the list. If we try to pop again, we have an empty result. Modules have types too, and these types are called signature or interface. We have seen in the previous example that OCaml infers signatures of module. But in fact, the programmer can force a module to have a specific signature. And in fact, he should do it, because publishing a well-designed signature is a very important communication aspect in a large project. And that will be the topic of the next sequence. So we have a syntax to define signature. You use the keyword sig, and between sig and end, you have declarations for the different components of your module. For instance, if you have a value, you use the keyword val, followed by the identifier of the value, colon, the type of this value. The other declarations for types and exceptions are exactly written in the same way as you can in a module implementation. A module can, in fact, contain other modules, so that we can create a hierarchy of modules. And similarly, a signature can also contain other module signatures. Now, if you want to refer to a submodule, you just have to use a path. So you have to extend the dot notation by just adding more module name to enter into the module namespace more deeply. It is forbidden to define two submodules with the same name in a module. But you can define, for instance, two values with the same name in a module. So, if you have defined a module forest, you can have a module tree inside to represent a tree of the forest, and in the type definition for trees, you can use here the type forest, which is defined before in the module forest. When we enter this to the OCaml top level, we can observe that the signature of the module forest contains another signature for the inner module tree. If we want to access to this namespace, we can just write open, and after that we can construct a leaf of a tree.